Good morning, everybody. Apologies for that technical difficulty. We are going to begin right now. Let us kick off with Lasec's liquid handling webinar. Welcome to all our participants joining us from all over the world. Warm welcome from all of us here in Cape Town. Today, our presenters will be sharing some guidelines and tips on general liquid handling, which will cover topics such as selecting the correct pipettes and tips, as well as recommending pipetting techniques to improve the overall accuracy, precision, and reproducibility of your results. The webinar will also briefly cover preventative maintenance and care of your pipettes to ensure their longevity and avoid common contamination issues. Next, I would like to share our new corporate video demonstrating Lasec's vast capabilities.
Founded in 1945 and operating out of South Africa with our head office here in Cape Town, Lasec has for the last 75 years been supporting customers both in South Africa and throughout Africa with dependable laboratory and scientific solutions. We work across public and private healthcare, research and manufacturing communities. This is our office space, which has recently been renovated. We have raised it a floor to accommodate for additional warehousing space below. Our open product and sales floor allows for easy collaboration between our teams, ensuring quick turnaround times on inquiries. You'll see some open desks here. That's because we are still working from home a few days a week to ensure we keep numbers at the office at a safe level. Our support teams, IT, finance, marketing, tenders, and logistics are centrally located here at our head office. We have multiple collaborative spaces available. Our auditorium is the perfect space for on-site workshops and seminars with customers and suppliers. Our meeting areas are equipped with state-of-the-art video conferencing technology, which allows us to easily connect to all over the world. Our demo rooms in both Cape Town and Johannesburg are fully equipped to host customers for a hands-on experience with our product. Whether you are troubleshooting or need our expertise, if there's a new instrument you're keen to try out, we have the facilities to accommodate this. With just under 8,000 square meters of warehousing space, we work closely with our partners to ensure stock availability. Our supply chain is optimized to land stock at the best possible price, but is agile to allow for expedited shipments. Our product teams monitor the market to anticipate demand trends, and we forecast accordingly. Our cold storage facilities are monitored remotely 24 hours a day, which means that we are able to react immediately should a problem arise. Our service engineers are well experienced and some of the most highly qualified on the continent. We have 3 NSF 49 accredited engineers trained at the highest level of biological safety. This equips our teams to validate, service and repair all major brands of safety cabinets to ensure the protection of users. We are ISO 17025 accredited for volume, temperature and mass metrology, allowing us to calibrate pipettes, balancers and temperature equipment ranging from ultra-low freezers to ovens and furnaces. Our logistics team handle both our inbound and outbound shipments from and to all over the world. We have representatives from our freight forwarding partners on site who support the quick handling of shipments. At Lasec, we facilitate higher learning, maximizing the potential of our employees. We have to date assisted 84 of our Lasec family reach their dreams of a better education. Our intern program for aspiring young professionals with a passion for science has mentored 38 South Africans, of which Lasec has permanently employed 12. A quick overview of our core business units. Consumables. An impressive stock holding ensures the availability of essential everyday consumable products. We work closely with our customers on demand forecasting, and depending on your price point and quality pressures, we have multiple tiers of product available. Laboratory instruments. Our experience and buying power and strong relationships with manufacturers brings world-class technology to end users cost effectively. We offer a wide range of instruments applicable to a variety of laboratory environments. We also support installation, setup, and end-user training. Biotechnology. Our range extensively covers RNA, DNA, and protein purification. Our PCR solutions include technology for endpoint, real-time, and droplet digital PCR. We offer a wide range of immunoassays for clinical and veterinary uses. This includes ELISA kits, rapid diagnostic tests, and customizable tests for urinalysis and drugs of abuse. We also offer a wide range of microscopy stains and staining equipments to cover all fields of biology. Sample collection. We work with global funding partners on addressing sample collection needs throughout Africa, primarily for the diagnosis and viral load monitoring of HIV. Our kit packing facility here in Cape Town is ISO 13485 accredited. We also pack sample collection kits for HPV, TB, and COVID. These are 100% customizable. Laboratory furniture. Our team design, manufacture, and install fit-for-purpose, customized lab furniture, considering the application of the lab to ensure optimized workflow. Manufactured locally and shipped flat-packed all over Africa, our teams also support on installation. Lasec education. We manufacture mobile lab kits and science products for schools who don't have access to full laboratories, giving little scientists a hands-on experience. Offering educator training ensures these experiments are delivered with confidence and safely in classroom environments. We have offices in all South African major city centres, as well as additional support in some of the outlying areas. Our international team, who actively support sub-Saharan Africa and beyond the continent, are based here in Cape Town. Our sales teams and end users are supported by product managers who make up our consumables, instruments, and biotechnology teams. These product managers are experienced in lab environments and have received extensive training from our manufacturing partners.
Okay, before we begin, a quick mention of our house rules. All participants' videos and microphones will be remotely deactivated. If there are any questions during the presentation, please place them in the chat. All questions will be answered after all the presentations have been presented. Once the presentations are finished, participants are welcome to leave or may stay on throughout the Q&A session. Introducing the webinar panel of presenters. My name is Roz, and I'm responsible for business and product development within the consumables team. We have Cameron Hutchinson is our product manager for liquid and mass metrology, and Storm Erlang is our product manager within the consumables team, responsible for our tip portfolio. First up on our agenda, we have Cameron, who will be talking us through our liquid handling.
Good morning, everyone. I'm just going to ask my colleagues if they can see me. All right. Thank you for joining this webinar. And I do apologize for the technical difficulties that we're having in terms of the participants. But this webinar is being recorded, so we will make it available to those individuals that weren't able to join us. For this webinar, we're going to be talking about manual liquid handling, and we'll be covering the following 8 topics, followed by a Q&A session at the end. So diving straight into it with our time restrictions. All right, so before we can discuss pipettes, let's cover what is a pipette, what's its purpose, because this will really set the foundations for all the other information to follow in this webinar, and explain why accuracy and precision is so important. So a pipette, by definition, is a piston-operated volumetric apparatus. Okay, this just means that the movement of that liquid when you aspirate and dispense is a piston-operated movement. All right, but fundamentally, why do we use a pipette? A pipette is there for the transfer of micro volumes of liquid. Obviously, in liquid handling, there's many different ways to transfer liquids, but a pipette is there for the micro volumes. So we're talking about our microliters, which are extremely difficult to measure any other way, as well as providing high accuracy and precision. So the goal of using a pipette ultimately is to ensure that we have good reproducibility of our experiments, as well as repeatability in the experiments that we are conducting. Okay, so to understand exactly what a pipette is, or a pipetting system, I would just like to highlight, I have looked at the register of attendees and it seems like it is across the board. So I'm going to assume that we've also got individuals that are relatively new to using pipettes. So from the beginning, a pipette, when we refer to it as a pipette, is simply just the device itself. However, just using a pipette on its own is not sufficient and will not yield high accuracy or precise results. So we have to use it as a system. And what does that consist of? Well, it consists of the pipette itself, as well as an appropriate tip and a trained operator. And I've used the word appropriate because you will see as this webinar continues, there's a variety of different pipettes available to you for different sorts of applications, as well as a variety of different tips for different applications. And it is going to be incredibly important that the operator of that pipette is trained in what they are doing. So now that we've identified that a pipette is not going to work by itself, it works as a system, we can continue with the webinar and we will move on to the types of pipettes. So in the market, there's two broad categories of pipettes. The first category is air displacement pipettes, and the second category is positive displacement pipettes. These will be discussed in more detail in the following slide, but there are also subcategories. So for example, for an air displacement pipette, you might also get a single channel version, a multi-channel version. In positive displacement pipettes, you can also get a single channel version or what we deem a repeater pipette. So the two broad categories are air displacement or ADP and positive displacement PDP, and they vary quite significantly from one another in terms of what we would use them for. All right, so just diving into what an air displacement pipette is, like the name says, by moving the piston up and down in this pipette, it displaces a certain amount of air. The amount of air that's displaced by the pipette is equivalent to the volume that would then be aspirated. So all of our pipettes have a certain common features or constructions. The first being the piston, as you can see illustrated by point number 1 over there. The piston then sits in the shaft of the pipette, also known as the tip holder. The tip is then attached to that tip holder. And with an air displacement pipette, an important characteristic is that there's always an air cushion between the sample and the pipette itself and the piston. So that basically means that there's always a dead volume of air. So essentially, as you depress that piston, it displaces a certain amount of air. As you release the push button, that piston is going to return to its rest position or its set position, thereby causing a partial vacuum inside of that tip that's going to be lower than the atmospheric pressure outside the tip. This forces liquid into the tip, and it is extremely important that we maintain that vacuum. All right, so I hope that sums up how an air displacement pipette works. What is the working principles of a pipette? So for the guys starting out with pipettes, let's just discuss the beginning. So when you first get a pipette, you will make sure that you, first of all, select the right pipette for the volume you wish to pipette. It is then important to set that volume. So the volume is set on the volume counter assembly on that pipette where you see the dial. On an air displacement pipette or a positive displacement pipette, you can either use, for most brands of pipettes, the button assembly, or in certain cases, there is a thumb wheel that's also available. The thumb wheel is generally for finer manipulation of that volume setting. By setting the volume of the pipette, essentially what you are doing is you are determining where that piston is going to sit in the tip holder. This determines how much air is going to be displaced when you start pipetting, i.e. how much volume is going to be aspirated. In order to prepare for aspiration, we will push down the push button at the top of the pipette. This will move the piston downwards, displacing that air. On releasing that push button, it will then aspirate that solution into the tip. Okay, so essentially it is basically just the difference in well, the partial vacuum inside that tip that you've now created, as well as the atmospheric pressure outside that really causes all that liquid to be aspirating to the tip. That partial vacuum also ensures that the liquid is held in that tip. This is going to be an important factor when we start discussing positive displacements and the limitation of air displacement pipettes. Another limitation that I would like to explain with an air displacement pipette right now is that we are now working with an air gap or an air cushion. Air is subject to compression and expansion. So basically it's got elastic properties, all right? These elastic properties are relatively fine when we are aspirating aqueous solutions, things such as water or watery-based substances, but there are a lot of limitations when it comes to things that are more viscous. Unfortunately, the elasticity of the air inside the pipette doesn't provide a strong enough force for difficult or problem or non-aqueous solutions. All right. So I will now play a video just showing you a bit of the functions of an air displacement pipette and walking through what I am doing. So basically, I'm preparing the aspiration. As you can see, the plunger inside the pipette, when I prepare for that aspiration, it depresses down into the tip holder. As I dispense it, the liquid, it presses down again. And you can see that there was always an air gap between that piston and the sample itself. So that is the main principle of the air displacement pipettes. However, like I said, because of the elastic properties of that air inside the pipette, there are a number of limitations. And to overcome some of those limitations, they have designed positive displacement pipettes. So what is a positive displacement pipette and how does it differ? So the principle is relatively the same in terms of using a piston to aspirate and dispense liquids and to transfer those micro volumes of liquids. However, the positioning of the piston is very different to the air displacement pipette. So in order to alleviate any of the shortcomings with air displacement pipettes, we now use a physical plunger. We've removed that air pocket or that air cushion, thereby removing any of those elastic properties of that air mass, and we have replaced it with a physical plunger. All right, so you can think of an air displacement pipette as working similarly to a syringe. But in terms of a syringe where you're generally measuring milliliters of volume, you are now wanting to accurately measure and dispense or transfer microliters of volume. So that's the reason we are using it in the form of a pipette. Okay, so how the positive displacement working principles work, very much similar to the air displacement pipette, now with the piston housed in the tip itself. So this piston is now going to come in contact with your solution, and that's why positive displacement pipettes generally use what we call a capillary piston. This is a disposable tip, much like the air displacement pipettes, but it now has two parts, which consist of that piston as well as the tip. So you would use it in much the same manner as an air displacement pipette by setting that volume first. With a positive displacement pipette, you will be able to physically see the piston moving up or down in that tip, depending on what volume you have set. To prepare for aspiration, you will again depress the push button. This time you can visually confirm that the piston is at the base of the tip or the tip orifice, and then aspirate. So it is really important, or it goes without saying, that it is important that your tip is sufficiently submerged in the liquid you plan to aspirate. Should it not be, you will land up aspirating air, therefore affecting your accuracy and reproducibility, as well as your precision. To dispense, you simply push down on that push button until the piston reaches the end of the tip and visually confirm that all the sample has been dispensed. All right, so now basically it's a physical piston. So now that we've removed that elastic properties of the air displacement pipettes, it means that we can actually now pipette accurately and precisely a number of different problem samples. So in this video, I'm just demonstrating how the piston looks inside the pipette. So essentially it's now been removed from inside and placed into the tip holder, into the tip itself. You will see how it draws up that liquid, much like a syringe. And to dispense it, you simply do the same principles as you would with an air displacement pipette. So why would we choose a positive displacement pipette over an air displacement pipette? And why is it more common to see air displacement pipettes in a laboratory as opposed to positive displacement pipettes? The one reason air displacement pipettes are more popular is because they still cover 90% of your laboratory applications. A positive displacement pipette is really there to assist you in the 10% of applications where you are working with difficult or problem samples or non-aqueous solutions. All right, so air displacement pipettes would cover things like water, sucrose, tris, buffers, etc., and is perfectly adequate for that purpose. However, positive displacement pipettes, like I said, is more for your non-aqueous solutions. These are things with high viscosity, things that are quite volatile, corrosive, hazardous, radioactive, and more important, and as well as hot and cold. So hot and cold is one that I just want to explain, because why would there be an issue pipetting hot and cold samples with an air displacement pipette? So essentially, if we think of an air displacement pipette, like I said, there's an air cushion between the piston and the sample itself. You can think of that as a sort of micro environment, similar to the environment outside, but now it's a contained small environment. Because there's air in that environment, it is subject to expanding or contracting with hot or cold temperature changes. So by pipetting hot or cold samples, you can change the properties of that air mass inside of that pipette, thereby altering the pressure inside the pipette, and you could have an issue of a leaking pipette or inaccurate volumes being aspirated or dispensed. Okay. With the high viscosity samples, I'm sure a lot of you have experienced this in the lab. It is quite a common thing, especially when pipetting glycerol, whereby it is, first of all, very difficult to pipette or aspirate. It takes quite a long time. You get what we call blowback into the tip. And when we try and dispense that, it is near impossible to get all of that solution out of the tip. This is because of the high surface tension and density of viscous solutions, and that elastic properties of that air pocket, like I said, just cannot provide enough force to aspirate and dispense that solution properly. So just as an illustration with glycerol, I want to show you the systematic errors and random errors that you could experience either using an air displacement pipette versus a positive displacement pipette. We will discuss systematic error and random error at the end of this webinar when we start discussing performance attributes. But for this case, as you can see, with increasing viscosity, okay, from 0 to 100%, if you are doing this with a regular air displacement pipette, from the mid to high viscosities, you will see that there is a drastic increase in the systematic error and random error of your results. However, with a positive displacement pipette, although there is slight deviation, you are able to maintain a relatively constant systematic and random error, regardless of the viscosity of the solution. Okay, so in this video, I'm going to demonstrate this for you by pipetting glycerol using an air displacement pipette and just showing what tends to happen. So you will notice that it pipettes really slowly at first. If you should remove that pipette before it is done aspirating, we get what's known as blowback. If there was no filter fitted to this pipette at that moment, you risk getting sample into your pipette, leading to further contamination or damage of the pipette. Once I dispensed that solution, you can see that there was still some remaining in the tip, and you could pretty much try and dispense that as much as possible. You will not be able to get all that solution out. Conversely, with a positive displacement pipette, you will see that it's a relatively quick aspiration step. And when I dispense it, it is relatively easy to get most of that solution out. So with very high viscosity solutions, there will always be some left in your tip. But what I'm hoping that this video demonstrates is although there is some solution left in that capillary piston, it is still significantly less than an air displacement pipette. So you can expect your reproducibility or your precision, your accuracy, and further reproducibility to be a lot greater with a positive displacement pipette. So this is just a table summarizing how we would go about selecting a pipette. So like I mentioned, for aqueous solutions, such as the examples listed here, an air displacement pipette is more than sufficient. When it comes to biological samples, especially your DNAs, your RNAs, and your proteins, so work such as PCR work, air displacement pipettes with filtered tips are quite important. And the reason for the filter tips, as my colleague might discuss a bit later in this webinar, is because DNA and RNA and those sorts of proteins can, in certain instances, become aerosols. So the filter tips, although not a complete physical barrier to aerosols, limits the amount of aerosols that could pass into that pipette and cause contamination. However, you'll see with all the difficult samples down below, the viscous, volatile, hazardous, or corrosive, a positive displacement pipette is preferable. And just on the hazardous ones, so I will just discuss, I have discussed the viscous, so I'll just discuss the volatile, hazardous, and corrosive and why we recommend a positive displacement pipette. So when it comes to volatile solutions, I'm sure a lot of you guys have worked with acetone in the labs before, or even just in normal life, and you will notice very quickly the smell of acetone. So because it's volatile, it tends to vaporize very easily. Like I mentioned a bit earlier in this webinar, if you consider the air displacement pipette, that microenvironment, there's still room for the acetone or the ethanol to vaporize or evaporate into that air pocket, thereby changing the pressure inside the pipette. So for those individuals that have been pipetting for quite some time, I'm sure they would have noticed that what we experience with an air displacement pipette and pipetting volatile samples is that there's a lot of leaking and dripping from the tip. This is simply because we cannot maintain that partial vacuum inside the tip as the solution starts evaporating. However, that issue is alleviated by using a positive displacement pipette, because now we no longer have an air cushion. It is a physical barrier, so there is no room for that volatile solution to evaporate any further in the tip. This will eliminate the leaking. When it comes to hazardous samples, these are things that you do not want to contaminate either the work surfaces with or further pipettes. Things such as radioactive isotopes, bloods, infectious bacteria, or viruses. Although you can technically use an air displacement pipette for these samples, you have limited protection against getting any of these substances into the pipette. So with an air displacement pipette, the most protection we can offer is by using a filter tip. However, like I mentioned a bit earlier, a filter tip is still porous. It has to allow air to move from the pipette through the tip and vice versa. So depending on the size of these aerosols, there is still a possibility that it will move through the filter and contaminate the pipette or subsequent samples. So with a piston in the tip, it means that there is a physical barrier. There is no way that any of these solutions can reach the pipette. This means that you have relatively a good safeguard that once you have discarded that tip, there will be no carryover to subsequent samples, or that your pipette isn't or that your pipette itself is not contaminated. When it comes to corrosive substances, I'm not sure if you saw in the video, but most pistons are made out of a metal or a stainless steel composite. So basically, acids can be quite corrosive to these pipettes. Some corrosive solutions are also quite volatile. So they've got two properties. So they're corrosive, but they also vaporize quite readily. So you want to avoid that and thereby use a positive displacement pipette. All right. So we have covered the two broad categories of pipettes, your air displacement and your positive displacement. And then I said that there's further subcategories. So in these subcategories, you can also get motorized pipettes, you can get large volume pipettes, you can get robotic pipettes. All right. So these two pipettes or machines that are illustrated here, still work off what we call the air displacement principle, but they are going to be used for instances where there's a higher throughput, or there is a demand for higher accuracy, higher precision, and higher reproducibility and repeatability of those results. It also would be considered if there is a very tight time constraint on your pipetting. So when you are pipetting, a very common workflow would be to pipette into a 96 well plate or even a 384 well plate as we start progressing. As some individuals in this webinar, I'm sure, can relate, pipetting into a 96 well plate with a single channel pipette is tedious, as well as a multi-channel. Although that does speed it up, there is still a lot of room for error in the pipetting cycle. All right. So in such an instance, you would consider using an instrument that's going to limit that sort of error due to the pipetting cycles. Okay, so since we are all humans, we do suffer from fatigue, we do suffer from complacency, and you will see later in the presentation when I discuss performance attributes that human error contributes quite a significant amount to pipetting errors. So in this video, we'll just demonstrate the 96 well plate filler, just to show how it speeds up that pipetting cycle. What would take a good amount of minutes, if not hours, to pipette, you can now do in a matter of seconds. The advantage to this is that you now limit the amount of pipetting steps that human operator would need to conduct. And when I talk about pipetting steps or pipetting cycles, I'm talking about aspirating, dispensing, aspirating, dispensing, aspirating, dispensing. As you can imagine, in each of those steps, we have the possibility of introducing error in our measurement if they weren't paying attention. Maybe they're aspirating at different speeds. And this will also affect the reproducibility between different individuals carrying out the exact same experiment or task. So user variability is quite a big factor to consider. And by employing systems like these, you really limit that amount of user variability between your experiments. So as you can see, this machine is fitted with 96 tips, essentially operating as 96 individual pipettes, thereby allowing you to fill up a 96 well plate in a single step. So you will see that in terms of a pipetting cycle, we have now only used one aspiration step and one dispensing step, thereby limiting the possibility of you using either 96 steps, 8 steps, or 12 steps. Okay, that machine can also then be used for your 384 well plates, obviously completing it in 4 steps. So essentially what I wanted to get across is that it is really important, depending on what pipetting task you are doing, to ensure that you are using the right pipette or tools that are more beneficial to your process. So coming up, my colleague is going to speak about tip selection. So I'll pass over to her.
Thanks, Cameron. Good morning, everyone. So to begin, there are a large variety of tips in the market suited for different applications. Most pipettes have universal tip holders, and tips are mostly designed to be non-specific so as to fit a wide variety of pipettes in the market. Unfortunately, this isn't always the case. So it is advised that you check the compatibility of the tip with your pipette and the performance of your pipette and tip as a complete system. Some other terms you will often hear used when talking about tips are wide bore, gel loading, bulk versus racked, filter versus non-filter, standard versus low bind, sterile, which is used in microbiological applications versus non-sterile, and RNAs, DNAs, and pyrogen-free, which is required for molecular work. For many fields, an important aspect of any product being used is traceability, and tips, particularly sterile tips, are no different. Important information needs to be included on all sterile tips that require traceability, will be the unique batch or lot number, a specified expiry date, and label warning symbols which provide important information on the recommended use of the product, such as whether it may be reused, where it has special designations, such as being an IBD, and like in this case, where the material is recyclable. Going hand in hand with traceability is accountability. To ensure your suppliers can be held accountable should there be any product defects, it is always advisable to request their quality documents. These include ISO 9001, which just shows they conform to a basic set of standards, ISO 13485, which is required for the manufacturing of medical devices and IVDs, a CE certificate, if they have them, though in certain circumstances it may not be necessary, a certificate of conformance, which is an assessment of the integrity of their product, not specific to a batch, and then to tie in with the importance of your tips being labeled with the unique lot numbers, a certificate of analysis to verify the integrity of the specific batch of tips you have purchased and are using. And now we'll go back to Cameron.
Right, thank you, Storm. I did see in the chat that someone was having a problem with the sound, but I will recap just quickly on the importance of the different types of tips. So essentially what we wanted to mention is, or show, is that there is a vast amount of tips on the market available for pipettes. Some individuals using pipettes might only be familiar with one or might not be familiar with all the options available. So there is a vast variety. I do recommend that if you are speaking to a sales representative that you are buying for, to get an idea of what is available to you, or to explain what your application might be, and we may be able to recommend a more suitable tip or confirm if the tip that you're using is suitable. Okay, so like I said right at the beginning, pipetting, it's a system. So if the tip is of a poor quality, if the tip does not fit the pipette, or if the tip is not based for that application, that system is not going to work accurately or precisely. And that is exactly what we want to achieve by using a pipette, is that accuracy and precision and reproducibility for other results. Okay. So we are now going to touch on pipetting techniques, starting from the beginning, and what to do with the pipette. And this is basically for all those individuals that have been using pipettes for a number of years. This will be second nature to most of you guys, I hope. So this might just serve as a refresher for you. But for any of the individuals that might be new in the lab, might be using pipettes for the first time, I will go through step by step exactly what you need to do and how to identify the pipettes. So the first thing you're going to do is identify a suitable pipette for the volume you wish to aspirate or dispense. All right. So you will see that in air displacement pipettes, there's a vast variety of different volumes that you can choose from, because each volume has only a finite working range. Okay. So as an example, over here, we are going to be looking at a Gilson pipette. However, this is pretty much universal. So as a disclaimer, a lot of the content that I am discussing, although the images and the imagery is based on Gilson, all, if not most of it, can be used for all other brands of pipettes. So the fundamentals always remain the same. Okay, so for this model, we are going to be looking at the Pipettement G. If I had to pick this one off the bench, I will see a P, a number, and a letter G. Okay, all that simply means is Pipettement. So Pipettement is a trademark of Gilson, and that is why all our air displacement pipettes start with Pipettement, followed by a number. That number in most cases of manufacturing, or most manufacturer cases, is the nominal or the maximum volume of the pipette. So this is a quick indication to show you this is the maximum amount of liquid I can aspirate with this pipette. It allows you to then decide, can I use this or do I look for a different pipette? Where individuals might struggle is figuring out exactly what that working range is. So from an industry standard, a good rule of thumb is that a pipette can be used to 1/10 of its maximum volume. For example, if I was using a 1000 microliter pipette, I can safely assume that the minimum volume is going to be 100 microliters. If you are confused or not very good with the percentages, for pipettes, it's quite easy. You just remove the 0 at the end of the maximum volume, and there you have the minimum volume that it can be used for. I have just highlighted the 10 microliter pipette in this case, since it can technically be used to 0.5 microliters. You would expect that it could only be used to 1 microliter. However, in saying this, I do recommend that you try only use your 10 microliter pipette to 1 microliter as a good laboratory practice. I would rather suggest that you get into the practice of good habits and rather exclude some of the exceptions. If I were to try and pipette to 0.5 microliters and I have a 2 microliter pipette available, I would suggest that you rather use that pipette. Okay, because you don't want to get into a bad habit of changing the volume slightly less than what the pipette is certified for, because you risk breaking the pipette or the mechanism or taking it out of calibration by readjusting the volume counter. Okay, so I hope that clearly explains how to determine the working range of the pipette. We're now going to set that volume. So because of the way that these volume counters on the pipettes are structured, it is subject to an error called parallax. And parallax is essentially an error whereby you are looking at the display from a different angle and it will show a different reading. It's very similar to looking at a measuring cylinder that's not from eye level, for example. Okay, so it is extremely important that you face the pipette head on and you try and make sure that it is eye level and that you are looking at it directly. Okay, in some situations, they do also recommend to improve this is to rotate the pipette horizontally and actually hold it horizontally, looking at it straight on. All right, so that's going to be the first step, is making sure that you are accurately actually setting this volume to the mark on the pipette. In certain cases, the pipettes do have a sort of resistive volume setting mechanism. This is quite useful to allow you to feel when the volume has been set into the groove. But this is not common amongst every single pipette manufacturer. Okay, the other topic that we're going to discuss when setting the volume is the direction of that volume knob or the thumb wheel. So as a recommendation for improved accuracy and reproducibility, it is a suggestion that you always end in a clockwise direction when changing the volume. All right. This means that in most cases, if I am decreasing the volume on the pipette, I will be rotating that knob to a clockwise direction. I will demonstrate this in an upcoming video, but right now I'm just going to explain it to you. You will rotate it in a clockwise direction as you decrease that volume. Obviously, wanting to end in a clockwise direction, you will decrease that volume to exactly the mark that you want it to be. All right. Should you overshoot that or undershoot that mark, you are going to have to rotate back up, which means that you are now rotating in an anti-clockwise direction. Since you want to end in a clockwise direction, you will have to decrease that volume again. So if I was increasing the volume, to recap, if I was increasing the volume now, I'll be rotating that knob in an anti-clockwise direction, meaning that in order to finish in a clockwise direction, I would have to exceed the maximum volume that I am wanting ever so slightly by about 1/3 of a turn and rotate the pipette back down to the volume that I want to set, thereby ending in a clockwise direction. So I'll demonstrate this for you in the video and explain it as we go along. Right now, I am decreasing that volume. You can see that I am turning that thumb wheel, if I was looking at it head on, in a clockwise direction. As you decrease that volume, you will see that that plunger or the piston is moving further down in the pipette. Essentially, what this is doing, it is reducing the amount of air pocket or air space in that pipette and reducing the amount of air that's eventually going to be displaced by the plunger. Like I said right at the beginning, when explaining air displacement pipettes, the amount of air displaced by that piston is going to be equivalent to the amount of liquid aspirated. So you can assume that when you're decreasing that volume, the piston will be moving down. Conversely, if I was increasing that volume, I would need to increase the amount of air that's going to be displaced. So I would need to move that piston into its full position. This is also why when changing volumes, it is incredibly important that you stick within the working range of the pipette. Should you exceed the working range, you may risk breaking the pipette by moving that piston further than where it can be. And therefore, you basically throw out all the accuracy and precision that you would have with that pipette. Okay, so I hope that that video nicely showed you guys exactly how that piston moves up and down. As I was increasing that volume, it was in an anti-clockwise direction. I then had to pass it and rotate back clockwise down to the set volume that I wanted. Okay, the next step in the pipetting techniques is fitting the tip. So this is quite an important one, and it also goes back to selecting the appropriate tip for that pipetting system. And when I talk about appropriate tips here, tip holders for most pipettes are designed to be as universal as possible, unless such a manufacturer has tried to make a lockout sort of model whereby you are locked into buying only their tips. But for the most part, most pipette manufacturers realize that there's a vast amount of tips on the market and that their pipette tip holders need to be as universal as possible. In saying this, it's not always the case that we can have every single tip fitting every pipette perfectly. So it is a general recommendation that you do consider using the manufacturer's tip, because this basically assures you that it is going to fit the pipette and it is going to guarantee the best performance. And when it comes to fitting the tip, it also means that if you are using an appropriate tip, that excessive force will not be required in order to fit the tip. So simply for a positive displacement pipette, all you have to do is gently apply some downward pressure, ensuring obviously that that tip holder is lined up with the tip itself. In certain situations, especially in small volume pipettes, you'll find that those tip holders are very, very thin and therefore quite fragile. So before fitting that tip, just make sure that it lines up really nicely with that tip before applying the downward pressure. All you have to do is apply a slight downward pressure, and we just recommend a slight rotation. This should be sufficient to fit that tip. If you are finding that excessive force is required, consider using a different tip or trying a different tip. It may be that the tip that you are using just either isn't right for that pipette, maybe it's an incorrect volume. Alternatively, it might just be a tip that's not compatible. All right. What we do find, and I'm sure if there's any university lecturers or supervisors that are doing undergrad labs, I often see it in industry as well, is that people tend to bang and hammer their pipettes into the tip rack. Obviously, this is not recommended because you do risk throwing the pipette out of calibration, but more frequently, we land up seeing cracks or fractures to the tip holders themselves. Obviously, damaging that tip holder, you damage the vacuum inside that pipette, and therefore without a vacuum or a partial vacuum, you are not going to be able to aspirate. So you are essentially damaging that pipette. We do see it with the small volume pipettes that sometimes those tip holders, after being banged into the pipettes, they do slip and those holders now point in a 90-degree angle almost. So really try to avoid banging your tips into your tip racks. If you're finding that that is the only way to fit it, use different tips or more appropriate tips. Now we go to the tricky one, the multi-channel. The multi-channel, I do find with customers that it's more of a trust issue. It's a bit of a bad relationship with fitting tips onto their multi-channels. whereby you find that the center channels tend to be a bit looser, or the tips tend to be a bit looser on the center channels compared to the outside channels. And oftentimes what we find is that individuals will try to individually fit and make sure that those tips fit their pipette. Obviously, if we think logically about this, if I was using a multi-channel for sterile work, for example, I've now opened my tip pack. It's a sterile tip pack, but I am now touching the tips with my hands, thereby voiding that sterility. So this is not the correct way to fit your tips to a multi-channel. The recommended way is that you do a slight downward pressure and a very gentle rocking motion. Obviously not excessive. You don't want to bend any of those tips, but a rocking motion basically allows you to fit the first 4 channels and then the last 4 channels back and forth. And this basically ensures that your center channels will be fitted properly. Unfortunately, with multi-channels, and depending on what pipette you are using and what tip you are using, you might find that some tip boxes, although generally manufactured and structured so that it's in a 96-well format, might not line up exactly with your channels. So it is important to find a tip box or tips that do line up with those channels, whereby you can fit all those tips successfully. So again, we are not putting excessive downward force. I do also find that a lot of individuals tend to press down on the head of the pipette. This, you risk breaking the inside lip that holds those channels in place. Okay, so that is excessive downward force. And once that lip has been bent, you will find that as you try to aspirate and dispense, the entire pipetting channel will move up and down into that head. If that is the case, and that is what's happening with one of your multi-channels, it means that the lip has bent up and that pipette needs to be repaired. Okay. I'm just going to demonstrate fitting the tips quickly for you on a single channel. So very simply, put it in, slight downward force, and rotate. And now for the multi-channels. So very important, make sure that they are lined up before you try jamming them into those tips. And you do a slight rocking mechanism or method to ensure that all those channels are fitted. All right, so the next pipetting technique that we will be discussing is pre-wetting the tip. This is often a step that is forgotten in most often. We are generally taught about it at first, but it is not a step that most people remember, because I don't think emphasis is placed on the importance of this step enough. So why do we pre-wet the tip? So another term that you might come across is pre-rinsing. And the reason why I don't enjoy the term pre-rinsing is if you're rinsing something, it's got the idea that you are trying to clean something out or remove something from the surface. Obviously, with pipettes and using disposable tips, we assume that those tips are clean and not being necessarily reused. And so you're not rinsing it for that purpose. Instead, you are actually just pre-wetting the tip. So the reasons we pre-wet that tip is, one, to create a uniform contact surface between subsequent aliquots. An aliquot is basically, if you are pipetting a volume, you could dispense smaller volumes, for example, those would be called aliquots, or it could just be each time you dispense a sample from the pipette. Okay. Again, going back to the principles of air displacement pipettes and how they work with the air space between the piston and the sample. Like I mentioned, this is a micro environment and it is subject to change. All right. So by pre-wetting that tip, generally speaking, we recommend that you pre-wet at least 3 times. Essentially what you are doing, say, for example, you are using a hot sample versus a cold sample, you are priming that environment inside of the tip so that it's accurate between subsequent aliquots. So you are limiting the amount of evaporation, and the reason you are doing that is basically you are increasing the amount of humidity inside that tip. You are saturating that air pocket. It therefore cannot accept any more moisture, thereby protecting your sample. Your sample's not going to evaporate into that air pocket. You are going to be able to dispense exactly the amount that you had aspirated originally. Okay. Another example of where pre-wetting might be useful is to compensate for vapor pressure differences depending on what samples you are using. Just please do keep in mind that when pipettes are calibrated, we calibrate them to a very specific international standard. The standard will be discussed later in the presentation, but it basically dictates what we need to calibrate with. In this case, we calibrate with distilled or deionized water. And obviously you can imagine that in the lab, you do get different liquids or solutions that vary from the consistency of water, the density of water, the temperature of the water, etc. All these sorts of factors will impact the accuracy of your pipette. So by pre-wetting that pipette, you're also priming the pipette for the use of a different solution. What I would hope that becomes quite apparent in this section as well is that there are different tools available. If you are feeling like even after pre-wetting, you're still noticing some level of evaporation, some dripping, or some skewed results, you might want to consider a positive displacement pipette where we've eliminated any of the need to prime. Okay, the only reason to pre-wet a positive displacement pipette would be for the first point of creating a uniform contact surface for your solutions. So if you had to look at a tip, for example, under a microscope, there are microscopic, well, I wouldn't say defects, but differences between each tip. So pre-wetting it, you're coating the surface, inside surface of that tip, ensuring that subsequent aliquots are all exposed to the same sort of surface. This does then increase your reproducibility, it does increase your accuracy, and it can, in certain cases, add to about 2% or 0.2% of your accuracy if you do not pre-wet. Obviously, like I said, this is a step that is often neglected, but there are going to be situations where you aren't able to pre-wet the tip. This might be with samples where you have very little sample volume to work with. In this case, you would disregard pre-wetting that tip, but just keep in mind, if your accuracy is affected, it could be as a consequence of not pre-wetting. All right, I'm just going to have a sip of water quickly. Okay, so I'm hoping that the pre-wetting and all the other steps before actually beginning your pipetting process or your pipetting cycle all make sense. We are now going to go on to the basic principles of pipetting. So this is common amongst all brands of pipettes. The general mechanism, the way that we pipette, etc., is uniform across the industry. All right, so with your air displacement pipette, as displayed here, the reason we know it's an air displacement pipette is that we can see that the piston sits inside the pipette and that it is fitted with a standard disposable tip. The basic principles are all the same. There are two different positions when you are pressing down on that push button at the top. So that's indicated by that yellow button at the top of the pipette. So I'm just going to explain the three positions actually. So there's the rest position. This is basically where it would be if no one's handling the pipette. Then you get what's known as the first stop, followed by the second stop, or also referred to as the purge stop. So the reason for these stops is basically the first stop is going to be used in your aspiration step. How you would do that is when aspirating the sample before inserting the pipette into the liquid. So while you've got a tip fitted, please remember to always fit a tip. Pipettes won't work without fitting a tip, and you will damage the pipette if you get a liquid in. So always make sure you've got a tip fitted. To prepare for your aspiration in the forward pipetting mode, you will basically depress the button to the first stop before placing that pipette into your solution. You will then slowly and in a controlled manner release that push button back to its rest position. okay, thereby aspirating the liquid from the container that you are aspirating out of. In order to dispense the liquid, you will then put it over the vessel or the container that you are planning on pipetting into. You will initially go down to the first stop, all right, and you will wait about a second to let that volume settle in the base of the tip. And thereafter, you will depress to the second stop or purge stop. So the purge stop is essentially just an additional volume of air that the pipette accommodates in order to push out all of that solution. Because of that elastic properties of the air, it's got a very low force that it can actually exert. And this is why a purge stop is absolutely important with air displacement pipettes in the forward pipetting mode. It ensures that everything gets blown out of the tip. So what I do want to just bring your attention to is the angles at which we recommend that you hold the pipette. So whenever aspirating, so in this step number 1 or preparing to aspirate, as well as your aspirating step, it is important to at all times try and hold your pipette as close to the vertical as possible. There's 2 reasons for this. The first reason being that this is how, well, there's 3 reasons actually. The first reason being that this is how a pipette is calibrated, okay, in order to measure how much volume's actually aspirated. The second reason is that if you do hold it at an angle that is too far from the vertical, you risk aspirating more sample than you had actually set the pipette to aspirate, thereby reducing your accuracy of that pipette. The third reason, and this is a reason that I like to use, is it ensures that the sample is always at the furthest distance from your pipette as possible. So gravity will pull that solution down. It will ensure that there's a sufficient gap between the sample and your pipette. You can imagine, and I'm sure a lot of people experience this, with the larger volume pipettes where there's very little surface tension in that tip, the liquid is freely able to move back and forth in that tip. So even a slight inclination of that angle means that that volume moves up in the tip and it moves ever so close to the pipette. So you really want to eliminate any sort of damage or cross-contamination of your pipette. So that would be the third reason I suggest always holding it in a vertical position when there is liquid in the tip. Okay, so that will be important for your preparation and your aspirating step. However, with the dispensing step, because you already have all the liquid in the tip, so you've now essentially aspirated the correct volume, you can hold the pipette slightly off vertical up to about 45 degrees. This is generally to help dispense into certain labware. So for example, if you've got a plate, if you've got tubes where you cannot alter the angle of those vessels, you are forced to alter the angle of the pipette. However, if you are doing this, just make sure that no liquid is touching the pipette, or if you're using a filter tip, make sure that no liquid is getting onto that filter. All right. But like I said, it is always best to practice good habits and best habits so that you don't make a mistake. So if you are able to hold it in the vertical position when dispensing, and instead you rotate or you angle the vessel that you are pipetting into, that is what I would consider a winning solution. When it comes to dispensing, it's important that you dispense towards the wall of that vessel. The reason being is that we are trying to use the surface tension of the liquid and the surface tension of that vessel to really draw all of the liquid out of the tip. Okay, so always, as far as possible, try to do a side dispense. This will just ensure that as much liquid as possible is dispensed from that tip. Also, once you have dispensed the solution, ensure that your pipette is lifted out of the solution or out of the sample before you return the push button back to its rest position. If you return it to its rest position, you are just going to re-aspirate that solution. And just in the bottom of the screen, the bottom right, you will see recommended immersion depths. This is quite important for accuracy. As you can imagine, if you submerge a tip too deeply in a solution, what's going to end up happening is you're going to have that sample gathering on the outside of the tip. This means that if you do then dispense that tip, you risk having whatever's on the outside of the tip also being dispensed with that sample. And you can obviously imagine that affects the accuracy and the precision. So these are just terms that are always going to come up because that was the goal of using a pipette. So although these are recommended immersion depths, I wouldn't expect anyone to measure in their pipetting cycle how far they are immersing that tip. So really just use common sense reservedly, but just ensure that the tip is sufficiently submerged so that as you are releasing that push button, no air bubbles are forming or no vortexing is happening, and that you are actually aspirating sufficient sample. So you are basically just looking at what the minimum you can put that tip in and still allow you to aspirate. Keeping in mind that for really small volumes, what tends to happen, or you can imagine in a PCR tube versus a microcentrifuge tube versus just an open beaker of water. If we consider the surface tension of that liquid, you will find that the smaller the volume, the larger the meniscus that forms at the top. So a meniscus, just like in a measuring cylinder, is basically just the semicircular bit at the top that tends to form when we are pipetting or working in cylindrical vessels. So this is also something to keep in mind as you are aspirating. If you are aspirating out of a really small container, you may need to follow that liquid quite closely to ensure that you don't aspirate any of the air. Okay, so unfortunately with pipetting, although it is such a common routine task, we do fall into complacent habits, and it does actually require our attention to really get the best results out of the pipetting cycle. Okay, and last thing on this slide that I'm going to discuss, looking at these vessels, is just jumping back to part number 2, where we are aspirating. When we aspirate out of a vessel or a container, we always try and aspirate out of the center. The reason being is that we would assume that the center is the most homogeneous part of that solution. So say, for example, you had taken a microcentrifuge tube and you had vortexed it before pipetting. That vortex would form in the center. So we assume that whatever's in the center of that microcentrifuge tube is the most homogeneous, most mixed up part of that sample. So always try as far as possible to aspirate from the center of the vessel that you are pipetting from. Right, so I'm just going to demonstrate in this video the forward mode of pipetting, clearly illustrating your first and second positions. So you can see I went to the first position and there's the second position. Just notice the movement of that piston. In the second position, that piston moves down ever so slightly, and that is what's considered the purge step. It does not affect the aspirated or the set volume of your pipette. So forward pipetting, you've set a volume. If you are following the forward pipetting technique by aspirating from the first stop, it means that you are aspirating exactly the amount of liquid that you have set that pipette to aspirate. So that's an important concept to realize. There is another technique. So the opposite to forward pipetting would be reverse pipetting. And as you can imagine, if forward pipetting was to the first stop, reverse pipetting, we are now starting at the second stop. All right. So essentially with reverse pipetting, in terms of your vessel and your angle and your holding of your pipette, all of those remain the same. The only difference with reverse pipetting is you are now starting at the second stop and you will finish your dispensing step at the first stop. You can now imagine that if I'm only finishing at the first stop, there's no purge step, and there will always be liquid remaining in the tip. Also, by starting from the second stop, it means that you are telling the pipette to actually aspirate slightly more than the set volume, so that when you do depress that the plunger to the first stop, you are dispensing the exact amount of volume that you want. All right, so why would we use reverse pipetting over forward pipetting? So if you did pay attention to the slide in about the top right corner, just above the image, I have noted that reverse pipetting is for about 10% of your applications, whereas forward pipetting is for about 90% of your applications. which is very similar to using an air displacement pipette versus a positive displacement pipette. So reverse pipetting is generally employed where we are working with difficult samples. Okay, much the same as the samples for or suitable for positive displacement pipettes. The only other area where reverse pipetting is generally employed is if you're working with solutions that tend to foam or bubble. All right, so with a forward dispensing method, in order to get all of that solution out of the tip, you need to follow through to the purge step. Like I said, this purge step is just an additional amount of air inside the pipette that blows out whatever liquid's remaining. Obviously, in blowing that liquid out, you now introduce air into whatever it is that you have now pipetted, and that can cause bubbles or foams or foaming to take place. So reverse pipetting is one way of avoiding that bubbles and foams, because you will always have solution left in your tip, thereby meaning you're not going all the way through to that purge step. You aren't blowing any solution into or any air into the solution or the sample that you have just pipetted. In saying this, although there are merits to reverse pipetting, I hope by now you guys would be thinking that why not just use a positive displacement pipette? It eliminates any sort of errors with reverse pipetting. You can continue to forward pipette with a positive displacement pipette, and it basically counteracts any of the issues that reverse pipetting was designed for. All right. Over here, I'm going to show you a video of reverse pipetting. And what I hope will become clear in this video is the risks of reverse pipetting. So like I said, if you're starting at the second stop, you are aspirating more volume than what that pipette is set to. In this case, I was working at the nominal or maximum volume of that pipette, also the nominal maximum volume of that tip. So by reverse pipetting, I'm introducing more than what that tip can actually handle. In the first instance, I had a filter in that tip. And what then lands up happening is that sample reaches the filter. Obviously, once any samples reach the filter, it will be somewhat absorbed by that filter. You will lose volume, and therefore it will affect the accuracy of your results. In this latest demonstration here, I decided, okay, I'm not going to use a filter tip. Maybe I'll use a standard tip, 1000 microliter tip. But what happened in such an instance is because I'm aspirating more than what that tip can handle, the solution actually reached the tip holder. So you can imagine now I've got no protective barrier between my pipette and that sample. Now liquid is ingressing into that tip holder. It's going to cause corrosion over time. It's going to cause contamination, and you will see what different types of contamination that may cause a bit later in the webinar. So with the pipetting techniques being continued, we are now going to talk about your positive displacement technique and a forward pipetting technique that's employed here. The reason it's a forward technique is that the whole purpose of a positive displacement pipette is also to eliminate the need for reverse pipetting. So again, it's going to cover about 10% of your applications, those really difficult, tricky samples that you struggle with pipetting with an air displacement pipette. So just like an air displacement pipette, it has a rest position. That's just its normal state when not in use. It then has a first stop, just like a normal air displacement pipette. However, you will notice that the second stop is now an ejection stop. And the reason for this is there is no longer a need for a second stop. Remember, I said that the second stop in air displacement pipette is also known as a purge stop. Because we are not working with air anymore, we are working with a physical piston that's going to aspirate and dispense. So it's going to forcefully suck up and physically push out that sample. I no longer need a stop that's going to push additional air to force that sample out the pipette. So this is why you don't have a second stop with an air displacement pipette. Instead, they've replaced that stop with an ejection button. This also is a built-in ejector, so it allows you to actually pipette out of tubes, things that are generally quite difficult to pipette out of with normal air displacement pipettes. Positive displacement pipettes are really great for that because the tips are also quite extended to accommodate that piston inside the tip. So unlike a normal disposable tip, your capillary pistons are generally longer. They've got longer reach to get into those tubes. So much the same as a air displacement pipette, you'll prepare for your aspiration by going to the first stop. Unlike an air displacement pipette, you can now physically see the movement of your plunger. So it is a better telltale sign. You can visually confirm that that piston is reaching the end of the tip. So you are ready to aspirate. Again, you would do this step before placing it in the solution. You would then aspirate. You would insert that tip into your solution. Again, keeping in mind your immersion depth. You don't want excessive amounts of liquid on the outside of that tip. Once you are happy that it is submerged sufficiently, you can release that push button back to its rest position. The plunger will move up and it will physically pull in that liquid. Much the same as dispensing with an air displacement, you will then again depress that plunger until the liquid is forced out of that tip. What you will notice in step 3 is that I have not changed the angle of my pipette, or I have not recommended that you do change the angle. And also the angle of the vessel that we are dispensing into is also vertical, whereas with an air displacement pipette, this was held at an angle. So with an air displacement pipette where we were doing a side dispense to the side of that vessel, the reason being was to use surface tension to our benefit to overcome the shortfalls of that elastic property of the air pocket. We've eliminated that elastic property. We now have a physical barrier that can push with quite a bit of force all that liquid out of the tip. So there's no real need to side dispense. There's also no real need to then hold anything at an angle. Okay. And because there is no purge stop, it is just going to be a reset by releasing that plunger or ejecting that tip. So these capillary pistons are disposable. Obviously, with the pipette, with the piston coming into contact with your sample, any new sample that you introduce will be contaminated. So they are designed to be disposed of. Right. So just quickly about contamination and the different types of contamination that you might find with using pipettes. The first one is pipette to sample contamination. This generally happens over time or by misuse of a pipette by an individual, or in instances where filter tips aren't used. So there's no physical barrier. So what often happens is that there's either sample that gets into the pipette and over time either causes corrosion or buildup of other substances inside that tip holder. As you then move or pipette with that pipette, obviously inside that tip holder, there's a piston that is moving up and down. It risks dislodging anything that has been stuck to the inside of that tip holder. If you're not using a filter tip, you risk that being expelled. Obviously, you are blowing air in an air displacement pipette, so you risk expelling that contaminant through into your sample. So a filter tip does form a physical barrier against that, and that's why it would be recommended. But obviously, in saying that, I always recommend that you do treat the pipettes well and that you are cognizant of the work that you are doing as to not allow any sample into that pipette. The next contamination that we have is the sample to pipette. So very similar to the previous one. However, for this one, I just want to highlight aerosol contamination. So aerosol contamination is quite common with biological samples. So your DNAs, your RNAs, your proteins, etc. And in some of those steps, you're also mixing quite a bit. So you are rapidly changing the amount of air in that pipette. If you do not use a filter tip, you can see that there is no barrier between the inside of the tip holder and the sample. Any sort of aerosols that are formed within that tip will move into that tip holder as that piston moves back up to its rest position. Okay. Subsequently, if you then continue to not use a filter tip, any of that aerosol contamination that now sits inside of that pipette, you will contaminate subsequent samples. So if you're finding that you are constantly getting some sort of contamination, I recommend trying a filter tip first. If that still doesn't solve the problem, maybe look at using a capillary piston or a positive displacement pipette, thereby eliminating any sort of contamination from the pipette itself. So in the center image over here, you will see that there is a filter tip. However, depending on the size of those aerosols, like I mentioned, the filters still need to be porous. For an air displacement pipette to work, you need to have air passing through that filter in both directions. So it is not an airtight barrier. So if the aerosol contaminants are of a small enough nature, they can still pass through that filter. Okay, so it is a partial barrier. If you've only got access to filter tips, rather use it than not use it at all. However, if you want to be absolutely certain that you're not getting any contamination into that pipette or on that pipette, and it will not be passed on from sample to sample, use a positive displacement pipette. There's a physical barrier between, so the piston forms a tight seal with the walls of that tip. So there is a physical barrier. No liquid can actually reach that tip holder. With a positive displacement pipette, even if you accidentally lie it down while there's liquid in the tip, or even hold it upside down, because of that physical barrier, you have no issue of getting any liquid onto the pipette. So essentially, by doing this, we are saying that once that disposable tip is ejected, you eliminate any of that potential contamination. Right, and the last one in terms of contamination is sample to sample carryover. This is generally the easiest sort of contamination to avoid, and simply change the tips between different samples. Obviously, if you are pipetting the same sample and just aliquots of the same sample, you are not concerned about contamination because it is exactly the same liquid. From a cost point of view, it is preferable to use the same tip. However, if you are changing from sample A to sample B, they are vastly different. You do not want to contaminate sample B with sample A. So eject that tip and get rid of it and place a new tip that we would assume is clean and sterile if you are using sterile tips. Okay, so that's a very easy way to avoid sample to sample carryover. So some decontamination points quickly to discuss is now that we've possibly identified that we've got contamination existing in our pipettes, or we want to avoid contamination going forward, what is the best way of decontaminating my pipette? Okay, so for radioactive compounds, a detergent cleaning in an ultrasonic bath tends to help. And just as a precursor to this, these are general guidelines. These are general solutions that might work. It is your responsibility, because there are so many different brands on the market, different manufacturers of pipettes. They may use different materials to one another. It is extremely important that before you carry out these decontamination steps, before you take apart a pipette, that you do refer to the user manual of that specific pipette. If you do land up decontaminating it or taking it apart and it's not in accordance with the user manual, you risk voiding any warranty on that pipette, but also you just risk damaging that pipette and its materials and might have to purchase a new one. So always refer to the user manual, but these are just some general guidelines of how one can disinfect a pipette. So for viruses, bacteria, mycoplasma, and fungi, we recommend UV radiation. Okay. Most of the materials that all the quality brands of pipettes are made out of are UV resistant. You will find for the cheaper pipettes on the market that they may not be made out of such a resistant UV. Again, refer to the user manual and see what their recommendations are. But if a pipette can be subject to UV radiation, this is quite a good way to get rid of or decontaminate against viruses, etc. However, there is a limitation in that the UV cannot penetrate the inside of the pipette. So while it is a good means of decontaminating the exterior of the pipette, so perhaps once you are done working, if you've got a UV light close to the bench that can be contained, you can place your pipettes in this area and expose them to that UV light for a couple of minutes in order to decontaminate them before using them again. But this does not decontaminate the inside of the pipette, unfortunately. Okay, for those internal components, you would have to try and use a different method, perhaps also the bleach solution or a detergent or cleaner in an ultrasonic bath. In such a case, you would be required to disassemble that pipette, and only certain parts would be able to be decontaminated. So for most of the pipettes out there, the parts that can be decontaminated in any sort of liquid would generally be the tip holder and the connecting nut. So these are the areas that generally come in contact with the tip and have the highest possibility of transferring any contamination into your sample. So you can take those apart and decontaminate them. Please never stick an entire pipette into a cleaning solution. I know it sounds like it would be common sense, but there are instances where individuals submerge or they use excessive amounts of detergent or bleach or alcohol to clean their pipettes. This damages the inside functions of that pipette. It can damage the volume counter assembly in terms of the readings on the display, as well as cause corrosion to the piston assembly. Okay, so for DNA, RNA, and biological samples, this is the most commonly used is a 10% bleach solution, as well as UV radiation. I also recommend you get some PCR sprays, which are designed to remove your DNAs, your RNAs, all of those sorts of contaminants. And you do often get them in either a spray or a wipe, so kind of like your alcohol wipes, which is quite convenient for wiping down the outside of your pipette relatively quickly. Okay. And for aqueous solutions and buffers, a water cleaning is generally sufficient. And then for organic solvents and proteins, detergent or cleaning solution is fine. All right, so these are just general guidelines. Some manufacturers might recommend different solutions. These are not the only decontamination solutions available to you. There are others on the market, but these are basically the industry accepted means of decontaminating your pipette. Okay, so just recapping back on the decontamination. One technique that people employ is also autoclaving your pipettes. Please make sure that before autoclaving that you have checked that the pipette is autoclavable. And most times when we indicate what a pipette is autoclavable to, it will be indicated either on the pipette itself or in the user manual what parameters you can use for autoclaving, as well as what parts of the pipette can be autoclaved. Oftentimes the tip holder and connecting nut can be autoclaved, but in some instances, not the full pipette can be autoclaved. So if you do land up autoclaving a non-autoclavable pipette, you risk melting the internal components and therefore rendering the pipette unusable. Whereas if you do have a pipette that is certified fully autoclavable, this generally means that you can autoclave the entire pipette without having to actually take it apart or dismantle it. Autoclaving also is not a complete means of sterilization. So in addition to autoclaving, we would recommend that you start with a normal decontamination as listed in that table previously, followed by perhaps an autoclaving step. Okay, because autoclaving is not going to remove RNA or DNA, for example, from the sample. So when you're working with PCR or molecular work, it is not going to be sufficient to decontaminate that pipette. The next topic we're going to be discussing is performance attributes. So what would have become common during this webinar is my discussion of accuracy and precision. Obviously, again, this is the reason we are using a micro pipette, because we want to accurately and precisely transfer or alicot small micro volumes of liquid. So when we are looking at these performance attributes of pipettes, there's two performance attributes that come up most regularly that we look at, and that would be the systematic error and the random error. So if we look at the systematic error on the left-hand side, we can see that this is quite a predictable change in or deviation from what our set value is. So we can assume that our set value is the center of this bullseye chart. And that is what we have now set the pipette to. That's what we're expecting that we would aspirate and dispense with each pipetting step. However, based on our results, we can see that those measurements deviate by a certain amount each time. You can notice that this deviation is quite precise in terms of the measurements being quite close to each other. As an example, if I had set my pipette to 1,000 microliters, I could be getting 999, 998, 997 continuously. They are quite closely grouped, but I would know that that is not the volume that I had set. So it is precise, but it is not accurate. Okay, it is not what I wanted to pipette. So basically what systematic error is showing is how your measurements compare to your set volume, okay? And it's generally very predictable. How we would try and counteract that is by recalibrating the device. So we would readjust the device. So this might be an issue with the pipette itself. Maybe it has been thrown slightly out of calibration. We would basically readjust it so that in each aliquoting step or pipetting step, our results are lying closer to what our set volume is supposed to be. Therefore, we try and get it back to be as precise and as accurate as possible. The other error is random error. Okay, this is also referred to as either standard deviation or in some cases coefficients of variance. The only difference between standard deviation and the coefficient of variance is that when random error is is shown in terms of a microliter volume or error, it is generally referred to as standard deviation of those measurements. However, when you convert it to a percentage, we then describe it as the coefficient of variance. Okay, so this is basically indicated as the random dispersion of results. But if I had to tell you that this is accurate, but it is not precise, that's what we would be seeing over here. Although those data points are all displayed all over the show, you will see that if we apply statistics to these results, so we find that average value, okay, if I had to put maybe a lasso around those results and I pulled it closer and closer and closer, you will see that those results come closer and closer to the center, and that center was our set volume. All right, but at no point are these results precise. And ultimately, you want both accuracy and precision. So when it comes to random error, the way that we try to account for that is we either improve our technique, there might be human factors affecting it, maybe you aren't paying much attention between subsequent pipetting cycles. It could be that environmental conditions, like I said, you might be using hot and cold solutions, and all those sorts of difficult samples could affect this. And how do we sort of counteract for some of these random errors if we can't improve it by improving our technique and improving our environmental conditions, is to run these in triplicate or more per sample. Thereby you can average those results, you can apply statistics to them and get an average result with the standard deviation up and down from what that average value is. All right, so that's how we counteract for random error. Obviously, we try to pipette as best as possible. Further to that, we just run samples a lot more in replicates so that we can apply statistics to those results and get an average measurement. And the average measurement we would suspect would be close to more or less what we are expecting. Okay. So in the next slide, it's just going to show you the difference between accuracy and precision. So you can see with the first one, it's accurate in terms of averaging those values. It will get you more or less close to that set volume, but it is at no point precise. It is scattered, it is random, it is very unpredictable. The second image also, it is precise, i.e. those values, those data sets are very closely related to one another, but it is inaccurate. It is removed from what that set value is supposed to be. Ultimately, what we want is accuracy and precision. And I'm hoping that in this webinar, we have addressed some of those techniques and things to keep in mind when pipetting in order to allow you to pipette both accurately and precisely. All right. So on to the next section would be the preventative maintenance and the self-maintenance of pipettes. For anyone purchasing pipettes, I'm sure they would know that they are relatively expensive pieces of equipment, and they should be looked after, especially if you are investing in quality pipettes. These are pipettes that could last you upwards of 10 to 15 years. If you look after them properly, they will remain in good working condition. So the first things that we would look at when you are starting to use a pipette, as you go into either student laboratories or even into the working world or the industry, it is not always possible that you will be using a set that is allocated to you. So there might be instances where someone else or various other people are using the same pipette. You have no oversight of how they are using the pipette, how they are handling the pipette, etc. So it is incredibly important before starting with the pipette to actually do a general appearance check. This is to identify if there's any glaring defects with the exterior of the pipette. All right, so maybe the tip ejector is missing, there's a crack in the tip holder, maybe the volume setting has been overwound, so you are seeing 3 zeros instead of a number. This is a general appearance check that you could do relatively quickly and identify, is this pipette going to be suitable to use or not? After you've done the general appearance check, you have noticed nothing of any significance on the exterior of the pipette, it is now important to do a functional test. And the reason we do a functional test with an air displacement pipette is obviously the piston is hidden inside of the pipette. You aren't actually able to see the mechanism inside. So you want to make sure that the piston is still in good working order, that the seals and O-rings ensuring that that piston is seated firmly in that tip holder haven't worn out, and also that the tip that you are using is actually appropriate for that pipette. Okay, so the first thing that you'll look at is the volume counter. So once you've established that there's nothing wrong with the volume counter, you will basically test that to make sure that that volume counter moves evenly. So essentially what I'm saying there is that if you are setting it to 1,000, that you can actually move it to 1,000 and that all of the numbers will line up exactly where they need to line up. All right, that's one function test for the volume. You can then, if the pipette allows you to change the volume in more than one place, for example, with these Gilson pipettes, you can change it on the actual push button. You can also change it on the thumb wheel. It's important to check both of those. The next function test that you're going to do is by depressing that push button to feel the movement of that piston, to feel if there's any sort of resistance, make sure that it's a smooth motion, okay? With pipetting and decreasing those sorts of human errors or performance errors, it is important that each pipetting step is as smooth and controlled as possible, okay? If at this stage you do realize that it's incredibly difficult to depress that push button, or that the push button does not return to its rest position once you release any pressure, that's an indication that a mechanism inside the pipette is damaged and rendering that pipette unusable, meaning that it would need to be serviced or that parts would need to be replaced. So all these checks that we are doing is to ensure that as we start working with our samples, we aren't either wasting our time, but also making sure that it's going to be accurate, it's going to be precise. And in some cases where that piston's not moving properly, it means that it might be rusted, and those rust bits can fall into your sample. So you're also trying to avoid that contamination further down the line. If we've completed the general appearance check and the function test, and we are happy with everything so far, we will then proceed to a leak test. And a leak test is or serves two primary functions. The first function is to ensure that that tip that you are using fits the pipette correctly, that it's forming an adequate seal. Because of that partial vacuum that needs to be maintained, you need to have an airtight seal between the tip and your tip holder. The second function that we're testing is that piston again. Is that piston working correctly? Is it able to maintain and hold that vacuum inside of the pipette? So essentially what a leak test is going to show is either the liquid's going to be retained in that tip with no leaking, or you're going to have droplets forming slowly. If it's not too much damage, it might be a slow drip formation. If there is significant damage inside the pipette, it will actually just start running out. It won't be a slight drip. Okay, so to perform a leak test on a large volume or volumes over 1,000 microliters, you can basically, and I'll demonstrate in the coming videos, but you can just submerge that pipette, aspirate, and then observe if there's any drips. Unfortunately, with the smaller volumes, so volumes under 1,000 microliters, there may not be significant force to pull that out. The way that you would do a leak test is by aspirating the volume and leaving the tip submerged in the liquid for a short period and observing if that level of liquid in the tip decreases or not. Okay, and then basically you get to your final step. This is going to be for preventative maintenance, as well as for addressing any issues that you might have observed in the previous 3 steps. All right, so when it comes to disassembling the pipette, again, I'm going to recommend that you always refer to the user manual of the pipette that you are using, because they will instruct you in most cases on how to properly dismantle a pipette. When it does come to dismantling a pipette, this is talking about preventative maintenance. So in a lot of situations, people prefer not to dismantle their pipettes. I find that it is generally a student sort of thing. We don't want inexperienced users damaging that pipette. But in saying that, if you do have any ingress of sample into your pipette or your tip holder, you want to prevent any corrosion of that piston. And the best way of doing that is to dismantle that pipette, clean out the tip holder sufficiently, let it dry, and then reassemble that pipette. The cost of replacing a piston for higher end pipettes can be almost 50%, if not more, of the cost of the pipette. So you really want to avoid corrosion of this piston. In such a case, I do recommend that you dismantle it, removing that sample from the tip holder, avoiding any sort of further corrosion down the line. And in dismantling the pipette, you are not necessarily going to affect the calibration of that pipette. Importantly, only provided that you replace it with exactly the same parts that you took apart, okay? So because we calibrate a pipette as a system, as a unit, all right, we are accounting for any possible defects in that tip holder, for example, any defects in that piston assembly. And by accounting for those, we've now calibrated that system. It's now working as it was calibrated. If I were to replace the tip holder with another tip holder, it is possible that it might not have the same defects, or it might have greater defects, for example. So now we've no longer calibrated it for that assembly. So if you do dismantle it just to clean it out or perform preventative maintenance, you shouldn't need to worry about the calibration all too much, provided that you do it with care and you are gentle in the dismantling of your pipette. If you do decide to change parts, such as your piston assembly or your tip holder, you are going to be required to recalibrate that pipette. So once you've disassembled and reassembled that pipette, it is always advisable to then perform a verification test on that pipette, just to ensure that it is actually aspirating and dispensing a volume that you have set it to. All right, so in this webinar, we aren't going to get into how to verify and calibrate pipettes. That will be something that will either be done on request or at a later stage. So for this instance, we are just talking about basic end user preventative maintenance and care of your pipettes. So the following videos are just going to be me showing exactly what we mean by general appearance check, leak test, and then some cleaning and preventative maintenance on your pipettes. All right, so what I'm doing there is I'm checking that volume setting or the volume counter. I check both the thumb wheel, I check the head. And the reason I'm using a large volume pipette in this case is on purpose, because what we find is that there is a lot of damage caused by ingress of solution into large volume pipettes. because the filter that you saw at the beginning of this video was not fitted. So if you do have large volume pipettes in your lab, please go and check that the filter is actually fitted in the pipette. Like I said, the surface tension for large volumes in larger tips is not very high, so that liquid can move quite freely around. So this is why we fit the filter into the pipette itself as a last barrier to prevent a liquid from getting into those tip holders. So oftentimes you saw on that video the amount of corrosion that was present on that piston. That would render the pipette completely unusable. I then demonstrated how a new piston looks, and you will see that that has a very clean, very precise finish to it. That is what you are aiming for. You're making sure that there's the seals and O-rings are fitted, and essentially that that tip holder is clean. So do fit a filter to your large volume pipette, but the same principle can be applied to all other pipettes to make sure that they are working properly. The next illustration is going to be a leak test, and this is on a 1 ml or 1000 microliter pipette. Like I said, with the 1000 microliters, you can just simply aspirate that solution and hold it there for a couple of seconds and observe if there is any dripping or leaking. If you were using a volatile solution, for example, you would have instantaneously seen that droplets were forming at the base of that tip. Again, use a different pipette completely because an air displacement pipette is not suitable. With the smaller volumes, you would leave those submerged in the water and just check that that liquid level is not decreasing. And finally, we just come to the dismantling and reassembling of the pipette, as well as some cleaning that you can do. Right now, I'm dismantling one of our branded pipettes. Obviously, the way that this pipette is dismantled might differ to the way that you would dismantle your pipettes. What I'm doing is cleaning the exterior of the pipette with a 70% alcohol wipe, which is quite common and quite useful in cleaning the exterior of the pipette. For some areas that are harder to reach or that require a bit more effort, by dipping a toothbrush or a bristle in 70% ethanol solution, you can gently remove anything from the grooves on the pipette. All right, obviously we are limiting the amount of liquid. We are not dousing the thing in liquid or the pipette in liquid. We are simply using just enough to clean the exterior. Once you take the pipette apart, you will now have access to the piston, the tip holder, and the connecting nut. Should you have anything in your tip holder that you want to remove or dislodge, you can completely submerge these parts in an ethanol solution and mechanically shake that up a bit to dislodge any particles that might be in that tip holder. It is incredibly important that after dousing or wiping off or leaving the parts in the ethanol, that you thoroughly rinse it with distilled or deionized water. So water that we know does not have any particles or pollutants or contaminants in it, and that we let the parts sufficiently dry before we reassemble them. So in some cases with tip holders, if they are wide enough, you can get these bottle or bristles brushes that you can use to physically and mechanically remove any contamination inside of those tip holders. Generally speaking, with the smaller volume pipettes, you have a very narrow tip holder. They are more difficult to clean than your larger volume pipettes. Now, before reassembly, it is important that you ensure that the parts are sufficiently dry. So most people generally air dry their parts, so they might do this at the end of the day and leave the parts to dry overnight. If you are in more of a hurry or you want to be more thorough that it is dry, you can leave it in a low temperature oven and just let that solution evaporate off. And obviously that solution being your distilled or deionized water that you rinse the parts with. Once you have reassembled the pipette, again, we go back to the inspection and we are going to want to make sure that it is functioning correctly once it's reassembled. So we would perform a leak test. Okay, and finally to wrap up, you guys have now essentially conducted your own preventative maintenance to the extent that an end user can look after their pipettes. Further to this, pipettes would then need to be serviced and calibrated by an authorized dealer of whatever pipette manufacturer you are using. All right, so there are two types of calibrations or standards that most people calibrate their pipettes to. The first one is the ISO 8655 standard. This is the baseline international standard, which really governs how to go about calibrating piston-operated volumetric apparatuses, which covers or encompasses pipettes. It also encompasses bottle top dispensers, for example. So anything operating on that's measuring volume that works with a piston, this is governed by ISO 8655. With this being the baseline, this is how all calibrations are to be carried out. There are two methods that are widely accepted. The first method being the gravimetric, as you would have seen in our corporate video at the beginning of this webinar, which showed the calibration facility. We use the gravimetric method, whereby we weigh the amount of liquid that's being pipetted. Another method is the photometric method, although not as widely used. It is still covered in this, this ISO standard. All right, so also what this ISO standard does is it dictates what the maximum permissible errors are for certain pipettes. So this is basically for manufacturers that are making these pipettes, they need to ensure that all their pipettes are performing within these maximum permissible errors. Obviously, it is also up to the end user if they want to employ stricter limits on their pipette performance. They just need to make sure that their pipette is able to perform within such strict limits. So if you do have a certain criteria and you are sending your pipette in to be calibrated, you can mention what your criteria is, and thereby the pipette calibration technician can actually see if it is possible to reach those limits using your pipette, or whether a new or refurbished pipette might be necessary. Also, you get an international standard called ISO 17025, or more commonly referred to as SANIS in South Africa. All right, so although 17025 is an international standard, it's employed by many companies across the world. SANIS is more based on South African, but it is based on the 17025 standard. Importantly, 17025 does not dictate how a calibration is going to take place. Instead, a 17025 accreditation is a laboratory accreditation, which governs the general requirements and the competency of the people in a testing and calibration laboratory. So what SANIS ensures is that the laboratory that is carrying out the calibration has all the equipment certified to very strict criteria, and that the operators are competent in actually calibrating and pipetting, or in calibrating and testing your devices. It does not dictate how a calibration is to be carried out. So you will find that even if a certificate is SANIS certified or accredited, this is a lab's accreditation, the standard to which the pipette calibration is carried out will still be stated as ISO 8655. All right. So these are generally carried out by accredited laboratories, either accredited by the manufacturer of the pipette that you are using, perhaps they have received training at the manufacturer, or it is accredited to SANIS to test or calibrate your equipment. So this would be an external service, and generally speaking with pipettes, or according to the ISO 8655 method, and depending on the importance of the work that you are doing, it is recommended that a pipette be calibrated annually. So obviously you can imagine if it's for just an undergrad student laboratory where perhaps the results are not as important, you can just do a normal verification. But wherever results are to be published or used for forensic work, for example, always get those pipettes calibrated at least annually, in some cases biannually, depending on the importance and the amount of times those pipettes are being used. Right. And finally, I'm just going to play a video that sums up what we have discussed in terms of the pipetting cycle. I'm not going to talk through this video. I think there is some backing, and we have put through some words that you can read on the screen, but essentially it's going to show you the pipetting cycle as a nice, concise summary. All right, so for my section of the webinar, this is done. We will be taking some questions and answers that you guys are welcome to pass through to us. But I'm going to hand over to my colleague, Roz, who will be handling the questions from her side.
Thank you, Cameron. Thank you for all joining us today. We hope you found it quite informative. Just a note, we have recorded this session. So if you would like a copy of this webinar, please email Astrid Meyer, astrid.meyer@lasec.com directly. Although I do think because of the technical difficulties we had a bit earlier, we will be sending this webinar out to everybody who did register. So we're going to commence with the Q&A section now. You're welcome to leave, or you can stay on and listen to all the questions and the answers. Okay, we have a first question that was sent in advance yesterday. Although Cameron has already answered it indirectly, I am going to ask the question directly, and he is going to give us an answer. We had a question come through from a multi-pipette user. She says that when using her multi-pipette, it seems to create bubbles when she dispenses into the 96 well plates. The media used to culture the cells contains FBS and it tends to foam up. Do you have any suggestions on how to resolve this problem?
All right, so that generally happens with air displacement pipettes where you are doing a forward pipetting technique. I'm assuming that the multi-channel is an air displacement pipette. There's very little positive displacement multi-channels on the market. So if this is the case, and you are pretty much only limited to using a multi-channel, therefore are limited to using an air displacement pipette, you can then employ reverse pipetting technique, thereby eliminating that purge stop at the end, which is generally the step that introduces the bubbles. Just be careful though, if you are operating the pipette at its maximum volume, keep in mind that you might not be able to do reverse pipetting because you will aspirate too much volume into that tip and the pipette. So alternatively, what you can also consider is for the positive displacement pipette, where this is not an issue, is to use a repeater pipette. Although it is not a multi-channel, you can actually aspirate quite a large volume of liquid, sometimes up to 50 mils, and set the volume that you want to allocate into each well. So it eliminates any air bubbles, but it also allows you to quickly go through your plate to ensure that you filled all those 96 wells or 384 wells without having any air bubbles. I hope that answers that question.
Thank you, Cameron. Another question for you. Is it possible that the lab temperature or change in season can affect the pipetting accuracy?
So yes, that is a possibility. When you are pipetting, it is best to try and get the solution that you're pipetting as well as your pipettes to equilibrate with the environment that it's in. So in that lab environment, ideally, you would want that sample to come down to room temperature so that the air inside the pipette is the same as the air outside, so that liquid's not going to really interrupt or change the properties of that airspace. Obviously, working in the labs and stuff, we know that that's not always possible. Certain solutions have to be kept either cold, other solutions have to be kept warm. That's where pre-wetting would help with that issue. However, again, positive displacement pipettes really are less affected by the properties of those samples. You can imagine that one thing that's quite important for volume is going to be the density and the pressure. So with shifts in seasons, both your temperature and your pressure will change. And that could affect the density of your sample and therefore the volume, or if you are verifying it, it will affect the weight of that sample. So there could be a shift that could account for those sorts of errors, but generally speaking, we would also maybe see that more on a systematic error basis where it's still predictable in each pipetting step, but you can then calibrate for the season. So if you're finding that a pipette all of a sudden was working in the cold temperatures, now you're working in the warm temperatures, you can then calibrate that pipette for those conditions or for the most prevalent conditions to try and get it to work a bit more accurately and precisely. And that's why some instances you might want to calibrate your pipette biannually instead of just annually. So this also goes to just sample properties. For certain sample properties where it differs from water, there are instances where you can actually calibrate your pipette specifically for that sample. Okay, so you might know that the sample differs from water, so it's not going to pipette the same amount. We can calibrate it or adjust it to accommodate for that liquid, but then that pipette is only going to be accurate and precise when you are pipetting that liquid. So say, for example, you're using a hot liquid and it's always at that temperature, you can calibrate that pipette using that liquid. So it wouldn't be completely in accordance with ISO 8655, but there is an exception to the standard that allows you to do so. And you basically would have some sort of surety that it's going to be accurate and precise for that temperature at that, for that sample at that temperature.
Okay, someone has asked if you could give an indication of the price difference between air displacement pipettes and positive displacement pipettes.
Right, so this is quite a common question that we do get asked. There is not a significant price difference between an air displacement pipette and a positive displacement pipette from the pipette side of things. Generally speaking, where you will notice a cost difference is obviously with regards to the tips. With the positive displacement pipettes requiring capillary pistons, there's more plastic being used, and those tips are slightly more expensive than your standard disposable bulk tips. In saying that, however, from an overall cost perspective, because a positive displacement pipette is not going to be used for as many applications in the lab as a air displacement pipette. So like I said, we're probably looking at about 10% of applications, or for an individual, it might be 100%, but that does not form the tasks of most of the lab. You're not going to be buying as many capillary pistons as you would disposable tips. So from that cost perspective, the consumables are a bit more expensive. The pipette itself is not significantly more or less than an air displacement pipette. And also do keep in mind that with an air displacement pipette, we calibrate and adjust it because of the piston mechanism inside and that volume setting mechanism. Because there is no piston inside the positive displacement pipette, essentially, if you had to open that up, it looks like a clutch pencil mechanism that grabs onto that piston. It is the piston in the tip that is specifically made to a certain length and calibrated. So it's the tip that lands up being checked and calibrated. You don't actually have to calibrate a positive displacement pipette. The only cost involved in terms of running costs would be the servicing costs in case any parts need to be replaced. But in terms of calibration, there is no way to recalibrate a positive displacement pipette. So that's something to consider when looking at costs.
Okay, a very interesting question came through. When doing verification on an air displacement pipette, is it imperative to use distilled water, even though they are used for organic solvents such as acetonitrile?
So generally speaking, if you are doing, sorry, can you just say, was it an air displacement or just a?
Air displacement pipette.
Okay, so generally speaking, with those pipettes and organic solvents, we would classify those as the difficult samples that an air displacement pipette is not really suitable to pipetting. But if you were trying to verify this or calibrate it according to the standard or check it against a previous calibration, you would need to repeat exactly what they have carried out, in which case if they've used a distilled or deionized water, it is imperative that you do the same. However, if your question is, if we are verifying or adjusting our pipette for the use of this liquid, can we use it to calibrate? You can. But with organic solvents, I think you might struggle to get that accuracy, precision, and essentially the repeatability out of those results, just because of the properties of that sample.
Okay, next one. Could you explain briefly how verification of a pipette is done?
Right, so there are steps outlined in ISO 8655 for certain manuals by different manufacturers. They also outline the procedure, which is exactly the same as ISO 8655. I think what's important to just distinguish between is a verification versus a calibration. A verification and calibration are carried out in exactly the same manner. The only difference between a calibration is that you are doing an adjustment based on those verification results. So when you are verifying a pipette, you're just checking to make sure that it's doing what you expect it to do. And a calibration is once you've verified it, you've seen that it's not doing what it needs to do, and then you will adjust it and re-verify it and make sure that it is where it needs to be. So the basic rundown is it's quite technical, but one thing that I do want to point out with the verification, so if you are going to be doing the gravimetric method, essentially you will measure or you will set the pipette, aspirate that volume, dispense it onto a balance, and you're expecting to see a mass measurement. All right. So like I mentioned previously, density, pressure, temperature, they all affect sample properties. So these need to be accounted for, and it's very often that in verifications, this is not a step that's accounted for. So when it comes to properly verifying or calibrating a pipette, we use what is known as a Z factor. So you cannot simply convert a volume measurement into a mass measurement. In order to go from a volume to a mass, it is important that you use this Z factor. And that Z factor is determined by the temperature and the pressure in the room, or those environmental conditions in the room at that time. And basically you will take your measured mass, multiply it by the Z factor, and that is a way that you can convert that mass measurement into a volume measurement for you to check against. But simply converting, going from a mass, say 1 milligram, does not necessarily always equal 1 microliter. It really depends on the environmental conditions at that place at that time. So that's one important thing to keep in mind. For anyone else that is interested in how to go about a proper verification, you are welcome to email Astrid Meyer, and I will be able to send you a guide on how to do it, but I don't think time allows me to go through that entire process right now.
Okay, another question relating to decontamination. Is it wrong to use fogging fumes to decontaminate a pipette, for example, formalin, especially when working with hazardous microorganisms?
All right, so that is quite a tricky one. I do not see any issue with the fogging per se, except that if it is in the pipette, when you are decontaminating the inside of the pipette, you generally want to make sure that whatever you are decontaminating with has also been removed. So generally for internal, I'm assuming that fogging is used to try and penetrate inside that pipette. If we are doing an internal decontamination, it's important to actually take the pipette apart and get inside. So should you do a fogging, you can do so, but still rinse it in case any particles might remain on the inside of that pipette. And also make sure that you check that whatever agent you are using for the fogging is compatible with the material of that pipette and will not degrade or damage that material, especially maybe the piston assemblies or the plastics that are used in the pipette. But as for a direct answer, I would need to look into that. And if you leave your details, we can always get back to you on that one.
Okay, thank you very much, Cameron. We will definitely get back to you, Lundy, for that. That is a wrap for today. Just to reiterate, we will be sending out a copy of this webinar to everybody who registered. Please email Astrid directly, astrid.meyer@lasec.com. Okay, thank you, Cameron. Thank you, Storm. And thank you for everybody's time today.
Thanks everyone for listening to this webinar. I really do hope that you found it informative, and yes, all the best for your pipetting.
Thank you, everybody.